Hi, I'm Yeonwoo, and I'll be presenting our baseline approach for FLARE25 Task 5 using the model PaliGemma2. Let's begin with the environment setup. We use a GPU with at least 24 GB of free RAM and CUDA version 11.8 or higher. To run the project, you can create a Conda environment with Python 3.10 or higher and install the necessary packages listed in requirements.txt file. The dataset provided for 2D tasks consists of 19 different datasets. These include multiple modalities, including clinical images, dermatology, ultrasound, X-ray, and more. The tasks are classification, multi-level classification, detection, instance detection, counting, regression, and report generation. If you have seen the dataset, you would have noticed that there are validation public and validation hidden dataset. Validation public includes answers. This is for you to test your own model, but validation hidden doesn't include answers. You need to predict the answer with your model. Validation public dataset doesn't include instance detection and regression tasks, and validation hidden dataset doesn't include counting and report generation. Each task type is evaluated with different metrics, which we'll cover next. For classification, we used balanced accuracy, while for multi-level classification, we used micro-averaged F1 score, which means instead of calculating it for each dataset separately, we sum the true positives, false positives, and false negatives over all datasets first, and then calculate the F1 score. Detection and instance detection are evaluated by F1 score based on IOU greater than 0.5. Counting and regression tests rely on mean absolute error, which is simply the average absolute difference between predicted values and ground truth values. But if your answer is not a numeric value, this metric will be evaluated as infinite value. So keep that in mind. And report generation is evaluated with green score, which penalizes false or missing findings and incorrect severity or location. So the dataset is uploaded on Hugging Face. So we use the Hugging Face client to download it locally. First, you need to log in to Hugging Face client with your token and use this following command. This will save all data under the original dataset directory. And when you first download it, you'll notice that all image folders are compressed as zip files. So before proceeding with pre-processing, you must unzip all folders. And before training, we pre-process the data. This step includes image validation, ensuring that all images can be properly loaded and converted to RGB. And it filters out the invalid samples and applies sampling strategies. You can enter the max samples argument, so if you do that, it will apply the sampling. Then it formats the dataset for Hugging Face so that we can load it easily later and generates training and validation splits. After running the pre-processing code, you will have a separate folder named process dataset, and the structure will look like this. So the model we're using here is PaliGemma2 for this baseline. And specifically, it is PaliGemma2 10 billion pre-trained 224. It uses 224 by 224 sized images and has a vision encoder and a linear projection layer. And as LLM, it uses Gemma2 9 billion. For fine-tuning, you can easily tune the hyperparameters by changing the arguments here. And if you want to resume from a checkpoint, you can enter resume from checkpoint and checkpoint pass arguments. The fine-tuning code first loads dataset from Hugging Face load from disk format which is the format we used in the pre-processing stage. We used a custom PyTorch dataset and a specialized data collator to load the data properly. And we fine-tuned the model using 4-bit quantization and LoRa to make it more efficient. And once you're done with fine-tuning, you can perform inference. You can enter either public or hidden as validation time, then it will perform inference on the specified dataset. It will first recursively search for validation JSON files in the specified dataset directory and generate answers using the fine-tuned model. Here we use this prompt, which is the same prompt we used in the fine-tuning part. It fine-tunes and then it parses the answers. The PaliGemma2 model basically in the answer, it repeats the question first and then answers the question. So we first parse the question part here. And then we parse the answer based on the specified task type. For example, instance detection or detection, we parse the list or dictionary part in the answer. And the counting or regression task, we parse the numeric value in the answer. And if there's no numeric value, it returns 0 as the answer. Lastly, we save all questions in all data sets into a single JSON file for evaluation. So your answers for all questions should be in a single JSON file like this. Finally, the evaluation script compares the predictions to ground truths and calculates the evaluation metrics mentioned before. In this code, you can only evaluate the validation public dataset. So it first recursively loads ground truth JSON files from validation public directory and calculates the metrics based on the task types. So as mentioned before, for classification, we use balanced accuracy. Multi-level classification uses micro-averaged F1 score, and detection and instance detection uses F1 score based on IOU greater than 0.5. In counting and regression, we use mean squared error. Report generation, we use green score. We compare the evaluation results of the base and the fine-tuned PaliGemma2 model. Fine-tuned model achieved much higher performances on every task. However, the F1 score for instance detection is only 0.002. So I think this will be the most difficult task in this challenge. We will introduce some success and failure cases. In this multi-level classification example, the model predicted all the answers correctly. But in this example, the model predicted nodule and pneumonia, where the correct answer is old fracture and pneumothorax. And in this detection example, the model correctly predicted the bounding box values. You can see that the ground truth region here and the predicted region overlaps a lot, but in this case, the IOU is lower than 0.5, which makes this a failure case. In this instance detection case, you can see that it correctly predicted the bounding box of one chromosome here, but failed to predict the other one here. That concludes the main part of my presentation. To summarize, we implemented a full baseline pipeline for PaliGemma25 task 5 using PaliGemma2. From dataset preparation to fine-tuning, inference, and evaluation. The inference and evaluation code is also provided as call-out notebook, so you can run it step by step. Overall, the fine-tuned model achieves much higher scores than the base model, but shows poor performance in instance detection checks. So this could be a key area of focus for the challenge. So now I'd be happy to take any questions you may have. Thank you.
Okay, great. You saved 10 minutes, Yeonwoo.
Well,
Any questions from the audience? Okay, I remember you also prepared a collab, right? I remember you also prepared a collab tutorial, right?
uh, not exactly. I will,
Could you please open the GitHub repository?
sorry.
Could you please open the GitHub repository?
Okay.
Do you have a collab for this tutorial?
Yeah.
What is it?
So, the inference
Okay, could you
collab,
please
you can,
go through the inference and the evaluation pipeline?
yeah, so the inference you can run here. You can just click the open in collab here and then run the cells in the notebook file here. Okay. I think I can run the inference notebook right now. Also, I'll test it here.
No, you don't need to run
Oh,
it now.
don't need to.
Just go through the whole pipeline, then participants can get familiar with the inference and the evaluation pipeline.
Oh, okay. So in this collab, first you need to set up the set up and import the libraries. So you can install the libraries here. And import the required libraries. And then you need to, so for PaliGemma2, you need to have like an access to the model with your token. So first you need to log in to the Hugging Face client with your access token. And for me, I loaded all my data sets and checkpoints in my Google Drive. So I mounted the Google Drive here, and then you can set the arguments here. So basically you can just type the model ID, base model ID, and this is the Hugging Face repository that you can find my fine-tuned model on, and this is the base dataset path. So the where you downloaded the original dataset, and validation type, hidden or public, and predictions here. Which prediction app, where you will save the predictions, and what would be your output file name. And then there are some utility functions. So it recursively searches for the JSON files. So these utility functions are for that. And this is the answer parsing part, and this is the part you remove the question part of the answer, and you can perform a task-specific parsing. And these are the functions for task specific parsing. And you can load your model here. I use the quantization to make it more efficient. And then this is the prediction function. It loads the data and adds the image tokens and formats the question with the prompt and then predicts here. So this is the function and it actually runs the function here. Then it will do the inference and save the file in the specified output directory. And then for evaluation, you can see the notebook file here. You can also open it in Colab using this button here. And this provides the evaluation for all tasks. So you can, also as an inference notebook file, you can download the packages here, and you need to download the green score package to evaluate your report generation tasks. So you have to have this part to evaluate it with the green score. And then it has arguments also. So the base dataset path is where you download the original dataset and a prediction file, which you made in the inference stage, and the output file name, which will save the matrix JSON file. So this also, as mentioned before, will only evaluate on your validation public folder. So here is the functions used to load all the ground truth JSON files in the validation public directory. And this is just for the last part where you save all the questions in one single JSON file, and this is to match the samples between ground truths and predictions using the image name and question. Yeah, so this is the task-specific metric calculation function. So this is the IOU calculation function, which is used for detection and instance detection. You can see all the metric calculation for specific tasks and below here. Yeah. So this routes each task type to appropriate metric calculation. Yeah, here we match the ground truths and the prediction parts, and then calculate here. And then it saves all the metrics in a JSON file, so you can check it on the JSON file. Yeah, that's basically the pipeline.
Okay, great. We got some questions from the formal chat. So, Sahan, feel free to unmute yourself.
Okay, hello everyone. Thank you. So our first question is, will the green score computation be done on the evaluation platform? Because we need more than we need more than the allowed. Basically, the platform only supports 16 GB, but we need more for it.
The direct answer is no. We will do it locally.
We will do it locally.
Yes.
Okay. And can you tell us more about the Docker format and how we will submit through Codebench?
Great question. So for on the code bench, we don't the code bench is only for validation submission, which means you can just submit a JSON file. We also provide an example on the website. So for Docker submission, I think you also have a example, right?
Yeah.
Could you please show that?
Mhm.
So yeah, so the direct answer is on our website. We also provide a Docker example. For Docker submission, you can directly email us. We will run it on our side and get back to you on the performance.
Okay, so just to be clear, what about the JSON on Codabench? Can you tell us what is the difference?
Uh, yeah. So, could you please share the code advance JSON example?
Oh, yeah, I'll do it right now. Okay, so this is the production file that you need to submit on the.
So all participants can find this. I remember you have put it on the website, right?
Oh, yeah, right. Sorry. I'll just.
Could you please directly share your whole screen instead of close and sharing?
um Sorry. Um,
So open code bench, please.
yeah, I will, but like. Oh. So here you can see the ready to submit zip file, which is our baseline results. So if you click here, there is a zip file. You have to submit it in a zip file. Like you have to compress the JSON files into like in the folder that contains JSON file into a zip file and then submit it on the Codabench website. And this JSON file should include all the answers to the validation hidden questions.
Sahid, is this clear for the JSON file part, for the code bench submission part?
For the Codabench, yes. So basically, we prepare this, and the output would be this, but then once we prepare the Docker, we have to send it to you by email.
Yes.
Okay, and the GitHub repo has some samples that we can follow for the Docker submission.
Could you please show the Docker example?
Okay.
No, all participants can find this.
Oh, I haven't uploaded the Docker image yet.
Okay, so we will do it in 24 hours and provide a Docker example on the GitHub page.
Okay, that would be better because we just needed the sample to refer to, and then we can send it later by email.
Yeah, okay, sounds great.
Okay.
And all the baseline links are already on the challenge homepage. There is a tab namely baseline. You can find all the baseline repositories there.
Mhm.
Any other questions from the audience? Oh, one more question is, could you please introduce the model in detail? So basically, here the baseline is just like original PaliGemma2. We didn't make any modifications of the office of PaliGemma2. Okay, any other questions? Okay, great. And Leo, it's yours.